Okay, let's go ahead and get started. Good morning, everyone. Does anyone have any quick questions on the homework that they would like to look at? All right. So, just a quick announcement. Just quiz 2 is going to be on next week, covering lessons 4, 5, and 6. And you're still going to have the same 24-hour window, except it's going to be from Wednesday the 9th to Thursday the 10th. So, just so you guys are aware of that. So, you should have got an email about this already, but just so now you know that there are official details on that. So, okay. Some people will write that down, so I'll give you guys a second. Like I said, this is also an email that Hoi may send, so you should have already seen that. But anyways, all right. So let's talk about the concept that we're going to be seeing for basically now until late October, early November, something along those lines. It's called the derivative. So, to sort of give you guys some context as to what the derivative does. So, we have this function y equals f of x. So, the line of the form y equals mx plus b, passing through the points a comma f of a and x comma f of x, has slope what? So, if we harken back to high school algebra or whichever math class you saw this in. So if you remember the slope equation, what form did that have? What was the slope equation you guys learned in high school? Over?
x2.
Right. So if you guys remember from high school, you guys had slope equations of the form m equals y2 minus y1 over x2 minus x1. So, in the context of being given these 2 points of this form, we can say that the slope in using these 2 points is going to be f of x minus f of a over x minus a. So, in this case, f of x would be your y2, f of a would be your y1, and this would be x2, and then this would be x1. So that would be the slope that you would get for that case. So graphically speaking, let's see what that looks like. So let's put a here, and then let's put x all the way over here. So if we have this graph, say it looks like that. So that's your y equals f of x. Alright? So in this case, what we have here is that we have a, which is right here. So that means f of a will be right here. And then x will have height up here, f of x up here. So that means your height here is going to be right about here. So f of x. Okay, so now what I'm going to do is I'm going to draw 2 lines. So the first one, as per the equation here, is going to be the line passing through x and a. So, fingers crossed I don't screw this up. Ah, beautiful. Okay, so in this case, this would correspond to the line passing through these 2 points here. So in this case, this is a comma f of a, and this is a comma f of a, and this is x comma f of x. F of x. Okay? So that's the first line that I wanted to talk about. Now the other line is going to just touch this point here on the graph. So it's going to look something like this. Okay? So here's what we have. So we have one line passing through 2 points on the graph, and then one line touching just 1 point around x equals a. So it turns out these lines have precise definitions. So the line passing through a comma f of a and x comma f of x is called a secant line. Okay? So something like this you have already seen in high school. You may not have seen the phrase secant line being used, but you have seen such a line being used before. However, the more interesting one is the green one. So the line passing through just a comma f of a is called the tangent line. The tangent line at x equals a. Okay? So in this class, we're going to be focusing more on this second one here, the green one. So to give us some more motivation on how to work with the tangent line, let's go ahead and consider the following. So if we let x equal a plus h, as in this above equation here, then what do we get? So m, our slope, is going to equal what? So if we just let x equal a plus h, we have a plus h. So f of a plus h minus f of a. All that divided by a plus h minus a. So if we just let x equal a plus h in our above form, then we end up with this. Now, what you'll notice is that on the numerator, there's not really much we can do with it by itself. But if we take a look at the denominator, well, we notice that we can subtract a and a here. So these two go away. So ultimately, we're just left with f of a plus h minus f of a. All of that divided by h. So if we utilize this slope equation in this form here, this expression is what's known as the difference quotient. So difference quotient, sometimes abbreviated as DQ. Okay. So before we move on, one thing I'm going to mention here is that if we were to, say, draw another line, say, right here, or look at another point, say, right here, then what we have is that if we denote this as, say, a plus h naught, then their point's going to be right here. So if I were to draw another secant line, which I'm going to denote in blue, then, let's see. Okay. So what do we notice with this? So we notice is that if we let this x value here get closer and closer to a, so the distance between them gets closer and closer to 0, then what we notice is that the secant lines get closer and closer to what would be the tangent line, right? So if that's the case, then that says, all right, well, let's go ahead and focus on what happens if we let our h values get closer and closer to 0, since h would correspond to our sort of distance between x and a. So moving on to page 2 here. So now let h approach 0 as above to consider the limits as h approaches 0 of f of a plus h minus f of a divided by h. Okay? Then, as we mentioned before, a plus h, well, that just approaches a to get these. So, as we mentioned above, so if we go back here, so if we get close, if x equals a plus h, and if we let h get closer and closer to 0, then it looks like, since this corresponds to the slope of the secant line, then if we let h go to 0, then that still give us the slope of the tangent line. Okay? So this whole thing here, this whole limit of the difference quotient will give us the slope of the tangent line. And in the context of calculus, this is what's known as the derivative. Okay? And this has notation f prime of a. So the prime here denotes derivative computations. Then we have the limit as h approaches 0 of f of a plus h minus f of a divided by h. Or if you prefer to use x instead of a, you can. So, or f prime of x equals limits as h approaches 0 of f of x plus h minus f of x divided by h. Okay? So, these are two different ways of expressing the same thing here, essentially. So, in this case, this is known as the limit definition of the derivative. Okay? Okay, so any questions on any of that before we move on to our examples? So let's take a look at example 4 then. So we're given that the derivative of this function tangent of x is f prime of x, which is just secant squared of x. Now we're trying to figure out how can this be expressed using the limit definition of the derivative here. Okay? So if we look at the limit definition, it looks like we have three quantities that involve f in some way, shape, or form, or its derivative. We have f prime of x, we have f of x plus h, and we have f of x. So the good news is, this problem already gives us f and f prime. So we have f prime of x equals secant squared of x. And then we already have f of x, as we said, tangent of x. So then if that's the case, then what does that tell us about what f of x plus h equals? So if f of x equals tangent of x, then f of x plus h would equal what? So in this case, all we're really doing here is we're just replacing whatever's inside here, in this case x, we're just replacing that with x plus h, right? So all we have to do is, yeah?
Would it be tangent x plus h?
Yeah, so it would be tangent of x plus h. Okay? So like I said, all we're really doing is we're just replacing, so replace x with x plus h. That's all we're really doing with this step from here to here. Okay? So now that we have these three quantities, what we can do is say, all right, well, plug this into the limit definition is the same thing as, well, secant squared of x equals the limit as h approaches 0 of tangent of x plus h minus tangent of x all over h. So, if you want to express this sentence here using the limit definition of the derivative, this is how you would do it. Okay? So, any questions on that? Okay, so this example was mainly intended to be more conceptual, just so you had an idea of where things would be placed in the context of the limit definition. So now, the next two examples we're going to focus on are going to be a lot more computation heavy. So, in this case, with example 5, we're going to use the limit definition of the derivative to find f prime of x if f of x equals x squared minus x plus 3. So in the homework, what you'll notice is that this type of problem will be broken up into 4 steps. So we're going to go ahead, to be consistent with the homework, we're going to also break it up in those same 4 steps. So break up into 4 steps. Okay. So step A, okay. So step A is we just need to find f of x plus h. Okay. So we already have f of x is just this quadratic. So if we were to find f of x plus h, then as per our example that we did above, all we really need to do is just replace x here with x plus h. So if we were to do that with our quadratic here, what would we end up with?
It would be x plus h squared minus x plus h.
Right, so it would be x plus h quantity squared minus quantity x plus h minus 3. So this would be our, plus 3, my bad. So then this would be our f of x plus h. So what we'll do now is we're going to go ahead and expand and distribute some stuff. So with x plus h quantity squared, if we were to expand that out, we should end up with what? X plus h quantity squared is what?
X squared plus h squared.
You're missing a term.
XH.
Almost. 2xh. There we go. Okay. And then from here, this will be the quadratic part. And then for this part, well, you just have to distribute the negative to x and h. So you just have minus x minus h, and then plus 3. All right? So make that a bit less compact. So we have xh plus h squared. Okay? So step 1 is just this, and we're done. So, squared and plus. Okay. All right, so that's step A. So now step B is use this to find the numerator of the difference quotient. So we have f of x plus h minus f of x. So all we do now is just take our result from A and then subtract that with the original function. Okay? So we already have this part from step A, f of x plus h. So now all we have to do is subtract that with our given f of x. So we have x squared plus 2xh plus h squared minus x minus h plus 3. So that's f of x plus h. And then we just subtract that with our original f of x. So x squared minus x plus 3. Okay? So if we were to get rid of common terms, then what expression should we end up with?
2xh plus h squared plus h.
Plus h? So 2xh plus h squared. Or it's minus h, but because so as you notice, the x squareds, well, they cancel each other out, and so do the negative x's, and as well as the 3's, right? So what we're ultimately left with at the end of the day here is 2xh plus h squared minus h. So that's the numerator of our difference quotient. Now let's go ahead and use that to find the actual difference quotient. So step C, so f of x plus h minus f of x divided by h. So the good news is that, well, not only do we know what the numerator is from step B, but if you notice, all three of the terms of the numerator have a common factor of h on them, right? So, taking that into account, how can we use that to simplify this fraction here? What's that?
Take h out of the numerator.
Right, so if we factor on h, we have 2x plus h minus 1 over h. And then, well, you can factor out cancel out the h's. Should be just left with 2x plus h minus 1. Okay? And so the good news is that now that we have the difference quotient expressed in a relatively nice form, step D, all we have to do now is just find the derivative. And using the limit definition, based on what we have from step C, that'll be pretty nice and quick. So f of x plus h minus f of x, all that divided by h. So using step C, we end up with limit as h approaches 0 of 2x plus h minus 1. So if we just let h approach 0 here, we should end up with what? Yep, just 2x minus 1. And, well, that's our derivative. Okay. So, any questions on that? Okay. So I'll give you guys a second to write that down. Is anyone still writing that down? Alright, so here's what I'm going to do with the next example. So this example is going to be a bit long, so what I would say is that if you have like a blank side of paper you can use, then you can continue example 6 on the back of said paper. Or alternatively, if you have double-sided, which is okay, then what you can do is say, well, we're not really going to focus on this example during class. I'll just say you can try this on your own outside of class, and you can check the notes after class. So if you want, you can say, all right, well, if you run out of space here, you can just say, all right, well, so you can just say continue example 6 here, if you want to do that. So it's up to you, but I'm just doing this because example 6 is going to be quite long. So I'm just going to make you guys aware of that now. Okay? So with example 6, let's go ahead and take a look at what this is saying. So the goal is we got to find the equation of the tangent line to the graph of f of x equals 1 divided by 2x squared at x equals 1. So here, what you'll notice is that we have to find the equation of the tangent line. So this is going to be something you're going to see a lot in this class, like a lot. So what I'm going to say is that you'll see this type of problem a lot in 16010. So with these types of problems, you're going to want to break this up into 3 steps. 1, 2, 3 steps. Okay? So the first step is you're going to want to find slope of the tangent line at x equals a, i.e. find f prime of a. Okay? So what does that mean in this situation? So in this case, if we take a look at our problem statement, then what you'll notice is that here, a is just going to be some explicitly given value here in this context. A equals given number. So a is just going to be some given number here. So in this case, you're given that, well, x equals 1. So in this case, a should equal 1. Okay, so that's that bit of part of the setup. So in this case, since the only tool we have to our disposal here at the moment is using the limit definition, well, that's kind of what we have to use here. So in order to find the slope of the tangent line, it might help to first find the derivative. So take the limit as h approaches 0 of our usual difference quotient. So limit as h approaches 0 of f of x plus h minus f of x all over h. Okay? And in order to do that, we unfortunately are going to have to utilize the 4-step process that we utilized in example 5 again, except in this case with the different function that we have in this problem. So let's go ahead and do that here. So what I'm going to do is I'm going to sort of use dotted lines to indicate that all this work here is just for step 1. So So let's go ahead and do that. So in this case, let's use step A. So first step is find f of x plus h. So in this case, if we already have that f of x is just 1 over 2x squared. So given that, that should tell us that f of x plus h is what? Yep. 1 over 2 times the quantity x plus h, quantity squared. Okay. So for right now, that's all we can really do with this. I mean, we could factor this out or expand this out, but we'll be doing that later in a bit. So for now, let's just leave it at this point. So that's step A. Step B, well, that's just going to be find the numerator of the difference quotient. Okay? So in this case, we have, all right, so we already have 1 over 2 times x plus h quantity squared minus 1 over 2x squared. So this part's just from step A, and this is just the function that we're given. So by itself, it doesn't really seem like we can do much with this, just by looking at the fraction or the expression the way it currently stands. Because here we have one fraction that has one denominator, and we have another fraction with a completely different one. Yeah?
Oh, no, mind. I was going to say what we should do.
Oh, sure, go for it. What's up?
We should make the denominators the same. So multiply the other side by, by h squared.
Yeah. So in this case, we could say, all right, so continuing on from that, so we could say, all right, well, one thing we could do is sort of condense this down into one fraction by using common denominators. So common denominators. Okay. So if we were to use common denominators, that means we need to say, all right, well, what factors does the denominator of the first fraction have that the other fraction does not, and vice versa? So in this case, to have common denominators between both of the fractions, that means we need to say, all right, well, for the first fraction, what factor or factors does the first denominator not have that the second denominator does? So what factors here does the second denominator have that the first does not? X squared, right? So to have common denominators here, we should probably multiply and divide by x squared on the first expression. So 2x squared times x plus h quantity squared. Okay? And using the same reasoning here, what should we multiply and divide by on the second fraction? Yep, just x plus h squared. 2x squared times x plus h quantity squared. Okay? Alright. So then now that we have common denominators here, we can just go ahead and condense this down as one fraction, as we have x squared minus x plus h quantity squared on the numerator, divided by 2x squared times x plus h quantity squared. Okay. So now that we have that, let's go ahead and focus on how we can simplify this in any way. So the denominator here, well, there's not really much we can do, it seems like. So our best bet is to see how we can simplify the numerator. So I'm going to write this denominator here again. So here, how could we, if we were to expand out the x plus h quantity squared, then and cancel out like terms from that, what could we get from the numerator here? So if we expand out the numerator, then as we saw before in example 5, then it seems like we should end up with, well, x squared minus x squared plus 2xh plus h squared, right? Based on what we did in the last example. So based off of that, what would this simplify to? Let's give someone else a chance. So if we were to cancel out common terms, what would this simplify to?
2xh plus h squared.
Almost, careful. You still have a negative hanging out here.
Oh, negative 2x each.
Right.
Negative each.
So the x squareds here cancel each other out just fine, but because of the negative, you still have to distribute that into these two remaining terms here, right? So in this case, you should end up with 2x, or negative 2xh minus h squared. All right? So that's all we can really do with the numerator for now of the difference quotients. So now let's move on to step C. All right. So now that we have the numerator of the difference quotients, let's use that to get the difference quotient itself. F of x plus h minus f of x, all that divided by h. All right. So in this case, all we're essentially doing is we're dividing the step B result by h, or equivalently, that's the same thing as multiplying the result from step B by 1 over h. So 1 over h of negative 2xh minus h squared divided by 2x squared times x plus h quantity squared. Okay? So taking this into account, how can we simplify this? Go ahead.
You can try and take out a factor first.
Okay. So if we do that, then if we factor out a factor of h here, we have, well, h times negative 2x minus h divided by 2x squared times x plus h quantity squared, and then divided by h. So then if we were to cancel these factors of h out, then we should end up with, well, negative 2x minus h divided by 2x squared times x plus h quantity squared. So that would be step C. Okay. And then last but not least, step D would be what? So the limit as h approaches 0 of f of x plus h minus f of x divided by h. Well, that's the same thing as, based off of step C, the limit as h approaches 0 of negative 2x minus h divided by, well, 2x squared times x plus h quantity squared. So then if we let h approach 0 in this expression here, well, what should we end up with this? Give someone else a chance. So who has this limit here? Actually, no, go ahead.
Negative 1 over 2x cubed.
Almost. So if we let h approach 0 here, right, we have negative 2x divided by, because this h goes away, by 2x squared times x squared. So then you notice that, okay, well, the 2's cancel each other out. One of the x's cancels out on top and bottom. So ultimately, you end up with negative 1 over x cubed. as your derivative. So this would be f prime of x. Okay? All right? So now that we have the derivative as a function of x, that says, okay, if we were to let x equal 1, then that'll give us the slope of the tangent line at x equals 1. Okay? So slope of tangent line at x equals 1 is, well, f prime of 1 equals, well, if you just let x equal 1 here, you'll pretty quickly get that the value is negative 1. So in this case, this would be your slope, or if you want, you can call this your value of m here. So, in this case, all that work here, all this work, was just to get the slope of the tangent. So, yeah, it's a lot. So first off, any questions on any of this before we move on to step 2? I promise it gets much easier after this. So generally step 1 usually won't take this long in the future because we'll have a bunch of derivative shortcuts that we'll learn next time, which will make step 1 significantly nicer. But I'm just doing this here just so that way you guys still understand, why we're using the limit definition, where things are coming from, etc. So I promise this is the longest step 1 you'll see all semester. So if it's any consolation. And I also promise that this is the longest of the 3 steps because once we have the slope, getting the point on the tangent line will be relatively easy, and we can then get the tangent line from that. Okay? So again, we're just going to sort of skip this for now. And I'll say, if you can try this on your own after class, and I'll post the lecture notes so you guys can check it. So step 2. So find points where, zoom in a bit, find points where tangent line touches f of x at x equals a. Okay? So i.e., find a comma f of a. Okay? Because if we harken back to the picture that we had in the first page, then this point a comma f of a is a point on the tangent line that's also on the function. So that's the reason why we're using this point here. Okay? So as we stated before, a equals 1. So all we need to do is just figure out, well, what is f of 1? Well, the good news is that we're already given f of 1 in the start of the problem. That's just 1 over 2x squared, right? So if you just let x equal 1 here, well, you should pretty quickly get that your function value is what? Yeah, just 1/2, right? Because you just get 1 over 2 times 1 quantity squared, or just 1/2. So what that tells us is that the point on the tangent line is 1 comma 1/2. Okay? So that's step 2. That's literally all of step 2. So now, the good news is that step 3, all we have to do is take the slope and a point on the line and use that to get our tangent line. So step 3. So find equation of the tangent line. Okay? So the thing is that some of you may be exposed to working with finding equations of lines using the slope-intercept form. And while that's certainly okay, what I'm going to do in this class is I'm going to use the point-slope form instead. So slope-intercept form okay. So y equals mx plus b. To find equation of line, but I'll use point slope below form below, since it's generally quicker. Okay? Okay. So here's what that means. So point slope form, if you recall, this is the same thing as y minus y naught equals m times x minus x naught. Okay? And the reason I'm using this is because, well, that says, all right, we need to have the slope of the tangent line. Okay, I already got that. And x naught, y naught correspond to a point on the line. Well, step 2 already gave us that. So all we need to do is just plug everything in, solve for y, and we're good to go. So in this case, we have m equals -1, and point is 1, 1/2. So all this we got from step 1, the slope, and the point here we got from step 2. So all we need to do now is just plug everything in. So we have y minus y naught. So in this case, x and y are just variables. So we have y minus y naught. So the corresponding y coordinate will be 1/2. And then this equals, well, the slope of -1 times x minus x naught, the corresponding x coordinate of our given point. So we have x minus 1. Okay? So just so you know where everything is getting placed here. Okay? So if we were to distribute everything out and solve for y, well, what should we end up with here? So we have y minus 1/2 is going to equal, so if we distribute -1, we should end up with -x plus 1. So if we solve for y, we add 1/2 over to the other side to get what? -x plus what? What's that?
1.5.
Yeah, 1.5, or you can also use 3/2 if log kappa doesn't want you to use decimals. So, okay. So I know that was a relatively long example, but do you guys have any questions on any of that? So.
If you go back to step 1,
Oh, sure.
yeah,
Sorry, 1 second. I think she's still writing some stuff down. So what were you? I'll just listen. And you can. Okay. What was your question?
yeah, so in step 1, I see that, I'm trying to find it. I'm trying to find it.
So while he's trying to find it, do you guys have any other questions you want to look at?
What did you get the 1 over h for?
This part here?
Yeah.
Because we're dividing by h here, so that's the same thing as multiplying by 1 over h.
Oh,
So we're just multiplying by reciprocals essentially.
okay.
Okay. Any others? Okay. You guys can go ahead and take off if you don't have any other questions. Please make sure to wipe off your tables before you leave. And otherwise, I will see you guys on Monday.